Hello everyone, and welcome back to the SD-GCM tutorial series. In the previous video, we downloaded historical and SSP245 CMIP6 data from the Copernicus Climate Data Store. Before applying bias correction to future climate projections, we first need to determine which bias correction method performs best. In this tutorial, we'll compare several popular methods and evaluate their performance using SD-GCM version 2.1. Different bias correction methods can produce different results for the same climate dataset. A method that performs well for one region or climate variable may not be the best choice for another. Instead of selecting a method based on assumptions, it's better to evaluate several methods using historical observations and compare their statistical performance. Once we've identified the best performing method, we can confidently apply it to future climate projections. The first step is to define the calibration and evaluation periods. The observation period specifies the observed station data used for comparison. The historical GCM period specifies the corresponding historical climate model data. Finally, the evaluation period defines the period over which the corrected data will be evaluated against the observations. These periods allow us to test how well each bias correction method reproduces the observed climate. For our first experiment, I'll use the same period for calibration and evaluation. The observation period is from 1993 to 2012. The historical GCM period is also 1993 to 2012. Finally, I'll set the evaluation period to 1993 through 2012. This approach evaluates each method using the same data that was used during calibration. Although this usually produces the best statistical performance, it does not tell us how well the method performs on independent data. SD-GCM currently supports several widely used bias correction methods, including the Delta method, Quantile Mapping, Empirical Quantile Mapping, Quantile Delta Mapping, Detrended Quantile Mapping, and Scaled Distribution Mapping. We'll evaluate each method using the same dataset and compare their performance afterward. Now I'll run each bias correction method one by one. After each evaluation is complete, I'll add the results to the comparison table. This allows all methods to be stored together so they can be compared using the same statistical metrics and graphical outputs. Once all methods have been evaluated, we can inspect the graphical results. The time series chart compares the observed and corrected data over time. The CDF comparison shows how closely the statistical distribution of the corrected data matches the observations. The QQ plot compares the quantiles of the observed and corrected datasets, making it easy to identify differences across the distribution. Finally, the annual cycle shows how well each method reproduces the seasonal pattern throughout the year. By selecting different rows in the comparison table, you can quickly compare the performance of all evaluated methods. Now let's perform a second experiment using independent calibration and evaluation periods. This provides a more realistic assessment because the methods are tested on data that were not used during calibration. I'll set the observation period to 1993 through 2002. The historical GCM period will also be 1993 through 2002. Finally, the evaluation period will be 2003 through 2012. This approach is commonly used to evaluate how well a bias correction method generalizes to unseen data. Now I'll repeat the evaluation for all 6 bias correction methods using these independent periods. After each method finishes, I'll add the results to the comparison table. Once they're complete, we'll compare the statistical performance of the different methods and identify which one performs best under both evaluation strategies. Now, we have 2 sets of evaluation results. The first uses the same period for calibration and evaluation, while the second uses independent calibration and validation periods. Next, we'll compare the statistical indicators and charts to determine which bias correction method provides the best overall performance for this dataset. Now, let's compare the performance of the 6 bias correction methods. The upper 6 rows correspond to the first experiment, where the same period, 1993 through 2012, was used for both calibration and evaluation. As expected, this represents the best-case scenario because the methods are evaluated using the same data they were calibrated on. The lower 6 rows correspond to the second experiment. Here, the methods were calibrated using data from 1993 through 2002 and then evaluated on an independent period from 2003 through 2012. This provides a more realistic assessment of how well each method performs on unseen data. Let's first look at the overlap experiment. Among all the methods, the delta method achieved the highest Nash, Sutcliffe efficiency, or NSE, with a value of approximately 0.76. It also produced the lowest RMSE and the highest index of agreement. These results indicate that, for this dataset, the delta method reproduces the observed precipitation more accurately than the other evaluated methods. Now, let's examine the independent validation experiment. As expected, the performance of all methods decreases because they're being tested on data that were not used during calibration. This is a more challenging and realistic evaluation. In this case, the Scaled Distribution Mapping, or SDM, method produced the highest Kling-Gupta efficiency, or KG, and one of the highest indices of agreement. The QDM method also performed well, with the lowest RMSE among the evaluated methods and a balanced overall performance. One important observation is that no single method performs best for every statistical indicator. Some methods produce a lower RMSE, others achieve a higher correlation, while another may provide a better KG or PBIS. For this reason, selecting a bias correction method should not be based on a single statistic. Instead, it's important to consider several performance measures together and choose the method that best matches the objectives of your study. In this example, the delta method performs exceptionally well when calibration and evaluation use the same period. However, when independent validation is applied, methods such as QDM and SDM show more robust performance, suggesting they may generalize better to future climate projections. The graphical comparisons above also help confirm these results by allowing you to compare the time series, cumulative distribution functions, quantile plots, and annual cycles for each method. Finally, if you'd like to analyze the results further, you can export the charts, save the evaluation table, or export the results for AI assistants such as ChatGPT or Gemini to generate detailed interpretations and reports. Thank you for watching. If you found this video helpful, please like, subscribe to the AgriMetSoft channel, and turn on notifications so you don't miss future tutorials on climate data, CMIP6, and bias correction. See you in the next video.